a Chicago skyscraper hides a deadly flaw.
These problematic windows led to outrage.
A fuel storage depot goes up in a fiery inferno.
There was a scene of devastation. Smoke could be seen from space.
A championship stadium suffers a devastating collapse.
Many people knew of someone who was involved, so the impact was grave.
And a major Canadian bridge reveals signs of catastrophic failure.
There were cracks and fissures that seriously imperiled the bridge.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings. Some with deadly consequences. These catastrophes are every engineer's worst nightmare. When it comes to building big, engineers have to carefully consider every material they use. If a single one doesn't do its job, a catastrophe could be on the horizon. Like this bold build in Chicago that became famous for all the wrong reasons.
The tower was never in danger, but the same couldn't be said for the people below.
A standout structure with a fundamental flaw. And an engineering catastrophe that quickly turned to tragedy.
People wanted action, they wanted it to be fixed, and they wanted it to be fixed now.
Chicago. The Windy City is famous for its extreme weather and extraordinary skyline. Boasting some of the tallest and most iconic buildings in the US.
When you think about epic architecture, you may think New York, but Chicago is actually considered as the birthplace of the skyscraper.
As local journalist Lee Bay knows well.
But Chicago has more than a century of fine buildings, particularly downtown. The downtown is relatively compact. The lake on the east side, the river and railroad tracks on the west. So there's no place to go but up. So 3 of America's tallest buildings are right here in Chicago.
In 1972, insurance company CNA Financial opened its brand new headquarters in downtown Chicago. To stand out in an already crowded skyline, architects came up with a bold plan.
This building comes in the 1970s, so it's, as a modernist building, it's pretty late. So to make the building stand out in a city of great architecture, they did an unusual thing. They painted it this shade of red.
Dwarfed by some of its neighboring high-rises, the plan to get the CNA Tower noticed by its eye-catching paint job earned it a catchy nickname. Big Red.
You know, Chicago has one of the most distinctive skylines in the world, certainly in America, built out over the course of 100 years or more, actually more than 100 years. And as a result, you want your buildings to stand out. So there's high-rise buildings, low-rise buildings, and most of them are gray and maybe a little bit of white, maybe black. But occasionally, to make the building stand out, you put in a splash of color. So this is a great example.
It earned the name Big Red, and it's pretty obvious why. Its striking crimson paint job was designed to emulate the sun setting over Lake Michigan.
Big Red became an instant landmark, as architecture historian Rick Keel explains.
The architecture is modern architecture. Think steel and glass box. It is 600 feet, 44 stories tall.
The building was a box design made up of heavy steel beams with thick frames and around 3,000 recessed windows set back 38 centimeters into the frame. And it's these unique windows that would give Big Red a reputation. Because the dazzling paintwork wasn't Big Red's only defining feature. Each of the 2-meter by nearly 3-meter recessed glass panels was given a grey tint. designed to give the facade the ability to play with light and shadow.
Big Red has 3,000 windows, all sitting in recesses between the thick beam structure. It's simple, yet stunning.
Big Red had achieved its goal of standing out from the crowd, but within months, it stood out for very different reasons.
Almost from the beginning, there were problems with its windows. There are 2,900 windows in this building.
There were complaints about windows cracking. There were actually 2,000 complaints in those first 2 years.
The complaints weren't just from tenants within the building. In 1994, a passerby was hurt by glass falling from the 36th story. Several years later, on June 7, 1999, a large crack was discovered in a window on the 29th floor. A white adhesive film was applied as a temporary measure to the entire pane to prevent pieces from falling out. This was covered with a piece of black plywood that sat inside the frame to be fixed at a later date. But on October 8, 1999, the unthinkable happened. A piece of jagged glass, about the size of a cafeteria tray, fell from the 29th floor, hurtling down from over 100 meters in the sky.
A young lady is walking downtown to a job interview. In fact, she gets off the L that's roaring behind us. And one of these windows, one on the 29th floor, falls from the building, floats over the L track, and strikes her as she's walking across the street on the west side of the street, holding her young daughter's hand.
Tragically, the young mother died. In the wake of the disaster, engineers investigated why so many of Big Red's windows were faulty, so they could prevent this from ever happening again. The reason at first seemed simple: the Chicago climate.
Chicago experiences some pretty extreme weather, from hot summers to freezing winters. And as every engineer knows, materials used in construction of a building will always respond to changing temperatures.
But why, in a city skyline filled with high-rises, was Big Red the only building apparently failing to cope with the climate? Forensic structural engineer David Drengenberg explains.
If you look at any skyline in any major city, you'll notice that the majority of buildings are clad with some type of curtain wall made of glass, which lets light in. Glass expands and contracts with changes in temperature. So if a building is exposed to direct sunlight, you'd expect the glass panel to uniformly expand in all directions.
In an effort to make Big Red stand out, setting the glass panes so far back into the frame may have caused this catastrophe.
When a window is installed in a place that receives only partial sunlight, the portion of the window that is exposed to sunlight will heat up faster than the shaded portion. So now you have the condition where one part of the glass is heated, the other part of the glass is cooled, and that tug of war between the expansion effects of the heated glass can create internal stresses that can sometimes form a crack.
Big Red's windows were being subjected to a phenomenon known as thermal stress.
Thermal stress occurs when heat causes an area of one piece of glass to expand against a cooler piece, resulting in cracking.
The warmer area of the glass which wants to expand begins to push against the cooler area which doesn't, creating thermal stress. If enough thermal stress builds up, the glass will crack.
The center core of the window would heat up faster than the perimeter of the window. As it heated, the center core expanded, the perimeter of the window stayed the same, and so between the two, something had to give.
Because all the panels were set back, the glass that was in direct sunlight was heating up and expanding. But the glass in the corners that was shaded was receiving much less sunlight and contracting, causing the glass panels to crack. David Drengenberg demonstrates.
We've assembled here a demonstration model to show how cracks would be expected to propagate under these kinds of environmental conditions. The window is installed into an aluminum extruded frame, and the effects of the expected temperature conditions have been replicated by a heat lamp in the middle, a fan on the edge. We've used a time-lapse camera to record the development of a crack. Okay, let's run the test and see what happens here. Light on.
David's experiment exposes one side of the glass plate to warm air and the other to cold, similar to how Chicago's winter weather affected Big Red. It's not long before the thermal stress causes the glass to fail.
As you can see, we have developed a crack after exposing the window panel to a number of heating and cooling cycles. And as expected, the crack propagates from the exterior, and as is common in brittle materials, continues to propagate all the way through.
Glass is a brittle material, and once it begins to crack, catastrophic failure isn't far behind.
In Chicago, the eye-catching skyscraper Big Red had a catastrophic design flaw. Its unique setback windows were putting unexpected stress on the panes. Engineers realized there was nothing they could do to salvage the existing ones.
With such a tragedy, engineers were left with only one choice: to replace all 3,000 windows on the building, but this time with glass that could handle Chicago's diverse climate.
But swapping out 3,000 windows couldn't happen overnight, so a temporary safety measure was initiated.
Replacing all those windows was a time-consuming task. To prevent more of them from breaking before they could be replaced, a stick-on protective film was applied to hold the glass together in the event of a failure.
This thick, adhesive safety film is made up of micro-polyester layers and is often used on buildings in places prone to hurricanes. If the glass breaks, it remains securely attached to the anchored sheet until it can be replaced. Big Red's windows were replaced with new, thicker, heat-tempered glass designed to stand up to thermal stress. In addition, they introduced a new safety measure.
To this day, Big Red's windows are each inspected on a monthly basis to ensure that glass will never again fall from the sky.
When designing a new structure, engineers have to consider its surroundings, as well as what it's intended to contain. Get that equation wrong, and all hell can break loose. Like this fuel storage depot outside of London that went up in flames.
This was a truly explosive engineering disaster.
It was absolutely extraordinary. I've never seen anything like it. It was just such a huge wall of flames.
This was a disaster just waiting to happen.
With hazardous substances like these, there is simply no margin of error.
Across the world, every major economy relies on oil, massive amounts of it. And in order to ensure that supply is constant, it needs to be stockpiled.
Oil makes the modern world go round, but it's not just sitting there on tap 24 hours a day. It has to be extracted, refined, and crucially stored. But it's dangerous at every stage.
Storing oil safely isn't easy, as fire safety engineer Fatih Tarada explains.
Storing fuels, especially on a large scale, requires constant monitoring of how much fuel you've got, and also not just the liquid fuel, you also have to think of the volatiles, the gas as well, the vapor, where that's going. Because the vapor can actually be a lot more dangerous than the liquid fuel itself.
Around an hour outside of London lies Bunsfield, a facility especially designed to safely store dangerous liquids.
Bunsfield is one of the largest oil storage depots in the UK. It was designed to safely store up to 60 million gallons of oil and petrochemicals.
Like any facility of this type, safety is the primary goal.
All of the storage cylinders are surrounded by bund walls, physical barriers that contain the contents of the cylinders in the event of a spillage.
The bund walls are designed to have a greater capacity than the storage containers they surround. In the event of a spillage, all escaped liquids will stay in a controlled area. In addition, all storage containers are equipped with an array of level monitors and safety valves. However, even the most secure facilities can suffer from catastrophe. On Saturday, December the 10th, 2005, a routine delivery of fuel arrived at the Bunsfield facility for storage.
The filling team started to input petrol into the storage tank 912 as evening set in. And we're talking about a lot of fuel, so this was going to take some time.
The process seemed to be going smoothly until the early hours of the morning when something went wrong.
By 5:37 a.m. on December 11th, the level within the tank exceeded its ultimate capacity, and the petrol started to spill out of vents on the tank roof.
No safety alarms were triggered, and the highly flammable liquid continued to overflow unnoticed. After spotting an unexpected vapor cloud, a member of the Bunsfield team hit the alarm, which activated the emergency water pumps.
A vapor cloud explosion occurred almost immediately.
After this terrifying explosion at one of the UK's largest fuel storage depots, the blaze rapidly spread throughout the facility. David Mitchell lives near the site and remembers the horrors of that night.
My wife and I were in bed when we heard a huge explosion, which really made us jump. All the alarms started going off, smoke alarms and things, and my first thought was that a plane had crashed on us. It was so loud, and the whole house was shaking, literally shaking. I could see the curtains dancing around. And then the ceilings come down, and the walls started to crack. All the plasterwork was cracked, and all the ceilings in the kitchen had collapsed. At this point, I was in total shock because it just looked like the house had been destroyed. But my real thought was because I had a young family, was just to get out of here. When I came out into the back garden, all the windows looked like they were going to fall out any moment. And the top half was leaning over, and there was a huge crack across the top of the house there, and tiles would come off the roof. And in fact, you know, there was actually a hole. You could stand in one of the bedrooms and look up, and you could see through to the sky.
Chief Fire Officer Roy Wilshire and his firefighters were called to the scene.
They describe approaching the site and seeing trees blasted, dead animals, birds in the road, cars abandoned, a scene of devastation. And, as I say, there was almost 300 buildings damaged on the Maylands estate alone, and very severe damage.
The ensuing fire was the largest seen in the UK since World War II.
So I remember looking at Bunsfield over there and thinking it was absolutely extraordinary. I'd never seen anything like it. It was just such a huge wall of flames, because this is seconds after the explosion, so all the petrol had only just gone up.
The smoke cloud could be seen from space. The smoke cloud blacked out central London, so Victoria was like midnight at midday.
40 people fell victim to injuries, but fortunately there were no fatalities. The fire lasted 5 days, with massive amounts of water and firefighting foam required to bring the blaze under control. In the aftermath, investigators had to uncover what had gone wrong. They first examined the automatic safety features on the faulty cylinder.
The tank had two forms of level control: a gauge that enabled the employees to monitor the filling operation, and an independent high-level switch, which was meant to close down operations automatically if the tank was overfilled.
It was clear that the initial level monitoring gauge had malfunctioned.
There was no way to alert the control room staff that the tank was filling to dangerous levels.
Further investigation revealed that the independent high-level switch had also failed due to a missing component. The compromised switch mechanism, combined with a defective monitor gauge, caused the fuel to overflow and fill the area within the bund wall. However, the liquid fuel itself wasn't what actually caused the explosion. As the fuel came into contact with the air, molecules on its surface started to evaporate, forming vapor which began to rise.
The bunded wall you can see there is there to contain liquid. It's not there to contain vapor. So vapor would spread over.
A vast combustible cloud now filled the air.
This was a powder keg ready to go off. All it needed was a tiny spark.
Investigators believed that tiny spark was created only after fire alarms were manually activated. As members of the public and tanker drivers noticed the vapor cloud, they alerted site workers who hit the alarm, automatically triggering the firewater pump. Ironically, it's thought that a spark from this pump is what ignited the vapor cloud. With the fuel ablaze, another failure came to light, this time in the bund wall itself.
The bund wall contained another engineering oversight. Plastics and silicon had been used in its construction. The heat of the explosion caused these to melt, allowing fuel to escape the bund wall and subsequently the fire to spread.
Fatty Tarada was part of the investigation team that uncovered this catastrophic failure within the bund wall joints.
If you have a bund for a hydrocarbon product, you expect it to operate, especially in the case of fire, because that is the primary risk that you're designing against. So if it doesn't operate, if you have a fire, what's it there for?
The legacy of the Bunsfield disaster prompted many questions when it comes to the safe storage of fuel.
What should have happened, there should have been electronic alarms, there should have been computer alarms, there should have been human intervention, and none of those worked to stop that petroleum being pumped down.
All this has been factored into the rebuild of the facility, with particular focus on the bund wall containment system.
It was realized that not only did they need to contain liquid, any material used in the joints would have to be able to withstand explosions and fire.
After such extensive damage from the explosion and fire, the facility needed to undergo a lot of reconstruction. Not only that, repairs were needed across the surrounding areas.
Although the facility is once again up and running, the long-term impacts of the explosion at Bunsfield still linger to this day.
The environmental, social and economic toll was considerable. While no one lost their life, some have yet to fully recover from the effect of the explosion.
Whereas before, it was a catalogue of errors, and I can't believe that anybody would allow that sort of lack of safety to ever occur again. However, I'm hoping that everybody learned from the experience last time and that everything now is state-of-the-art and all the proper procedures are there.
When engineers get their calculations wrong, the consequences can be instantly catastrophic. However, sometimes it can take decades before an oversight comes to light. Like this bridge in Canada that hid its lethal design flaw in plain sight.
This engineering issue was overlooked for years.
There were cracks and fissures that would collapse the bridge.
A vital transportation link that put commuters at serious risk.
This bridge just wasn't built to stand the test of time.
Montreal was founded in the 1600s, a hub for fur traders, built up on the side of a small mountain that gave the city its name.
Named after the triple-peaked hill in its center, Mount Royal, the city of Montreal is sandwiched between the St. Lawrence River to the south and the Rivière de Paris to the north.
Montreal is actually an island surrounded by waterways. The only way on and off is by bridge. Local journalist Teddy Elliott explains.
Bridges are perhaps the most important element of the city because it connects the city to the United States, it connects the city to the northern part of Quebec.
In 1957, work began on the first Champlain Bridge, connecting the island of Montreal with the South Shore suburbs. The massive crossing would stretch for more than 7 kilometers, with long approaches leading to a steel truss cantilever center span, just over 3 kilometers long. The epic structure cost $52 million and incorporated a bridge deck design that made it truly cutting edge.
This bridge was designed in the 50s, and the material of the moment was pre-stressed concrete.
Pre-stressed concrete is made with tensioned steel members in or around it. These steel tendons significantly increase its tensile strength.
This allows architects and engineers to design and build lighter and shallower concrete structures without sacrificing strength.
The original Champlain Bridge opened in 1962. By the 1970s, it was the nation's busiest crossing. It ushered traffic to and from the city of Montreal for decades without any problems. But by the turn of the century, it began showing signs of failure.
In the late 2000s, they found that within the actual superstructure of the bridge itself, there were cracks and fissures that seriously imperiled the lifespan and potentially collapse the bridge if they continue to proliferate.
Cracks in the concrete and rust on the reinforcing steel cables were telltale signs that the bridge could be in serious trouble.
A thorough inspection revealed that severe deterioration was occurring across the entire structure. A worrying thought, given how many cars used the bridge daily.
Of particular concern was the degradation of the pre-stressed concrete decks on the bridge approach. Engineers investigated and discovered the cause of its untimely demise.
Montreal gets hot summers and very cold winters. Water finds its way into the smallest crevices, and as it freezes and thaws with the climate, it expands and contracts. And this process over time causes cracks to grow and the concrete to break.
The cracking concrete exposed the steel rebar inside to water. But the runoff from the bridge above wasn't just pure water. Engineer Steve Stelzer explains.
In our climate, we have a lot of salt that's used on the roads to clear off ice. We have a lot of freeze-thaw. We have very inclement weather. The weather can change drastically in a matter of a few days.
When you have cold, icy winters like in this part of Canada, roads and bridges are regularly salted to make them safe for motorists. When that salt dissolves into snow and rainwater, it runs off the deck and down the structure of the bridge. Once it comes into contact with any exposed steel in the pre-stressed concrete, it can only mean one thing: rust.
Rust occurs when oxygen and water react with the steel rebar, forming iron oxide. When salt is added to the water, it accelerates the corrosion by up to 10 times.
Over time, freeze-thawing in the concrete and rusting of the steel caused integral parts of the bridge to crumble and fall at a pace not foreseen by the engineers that built it.
And this process was made even worse by a flaw in its design. Professor of Structural Engineering Lotfi Guzani explains.
In this bridge, elements were integrated together, but there was not proper drainage system. Also, there were no waterproof membrane like in today's bridges. So salty water comes through the deck and attacks and infiltrates within the concrete and attacks the steel tendons, which pre-stress the concrete.
The long-term results of this slow decay can be extremely hazardous, as concrete surveyor Mark Vandry explains.
There started to be cracks and corrosion forming in the post-tension cables, in the rebar, that could have, over the long run, caused a catastrophic failure.
The way the bridge was constructed, the elements are integrated together. So if one beam fails, there's a large part of the bridge which will fail.
Montreal's Champlain Bridge was deteriorating much faster than engineers had ever anticipated. With the corrosion advancing, a solution was urgently needed. Plans were made to replace the bridge, but that would take years to complete. In order to keep traffic flowing, the pre-stressed bridge approach decks were reinforced with what was dubbed a super beam.
The super beam was a large steel beam that was placed over the concrete beam on the bridge deck, which allowed them to keep it stable.
You're basically creating a structure to support another structure. So they created these super beam trusses to support parts of the deck. Now, the problem with this type of fixing with super beams and trusses, fixing parts of the deck, you're redistributing the load patterns of the way the structure was meant to act. And what happened is that it caused cracks and other structural problems in other parts of the deck.
To maintain the old bridge until the new crossing could be built, it also had to undergo regularly scheduled repair work.
Ultimately, choosing concrete for the deck and girders proved to be the wrong choice. Concrete is difficult to repair effectively, and patching it up will never last.
One reason that concrete was chosen was that it could be pre-cast, speeding up the bridge building process. But although pre-stressed concrete was innovative for the time, it turned out to be a maintenance nightmare.
The steel would have been a better option because when they chose pre-stressed concrete, this technology was not mature and they have a lack of knowledge about the durability issues.
It's just not suitable for our climate for bridge work, where there's lots of salt, lots of drainage problems, there's corrosion. With pre-stressed concrete decks and girders, once it's in, it's very hard to reinforce it and go in and actually fix it.
Steel can be easily cleaned, reinforced, and have extra strengthening elements welded to it.
With the old Champlain Bridge scheduled for demolition, back in 2015, work began on its replacement. The new crossing opened to traffic in July 2019, a 168-meter asymmetric twin cable stay bridge. Costing $4 billion, this epic piece of engineering carries 6 lanes of traffic, and with a width of approximately 60 meters, it's one of the widest bridges in the world. With the use of cutting-edge design and, crucially, the right choice of materials, the new Champlain Bridge is designed to survive Montreal's tough weather for 125 years.
Hopefully, Montreal's new crossing will keep traffic flowing smoothly and, more importantly, safely for decades to come.
With big engineering, careful planning in both design and construction is usually the secret to success. But get either wrong, and it can be a recipe for disaster. Like this catastrophic collapse in Holland, which exposed critical flaws in construction.
Fundamental engineering errors and communication failures led to a fatal collapse.
A stadium tragedy that shook a city to its core.
It gets emotional when something happens, and why us?
The lessons learned from this failure serve as a reminder of the importance of coordination, communication, and checking.
In the central region of the Netherlands, known as Twente, lies the medieval and picturesque city of Enschede. With a population of just over 150,000, the beating heart of this town is its soccer club, FC Twente.
FC20 from Holland are a top-flight soccer team based in the Dutch city of Enschede.
As local journalist Bart Hinke explains.
FC20 is a club that's deeply rooted in this region. They have about 28 supporters, fan clubs in the region, and you can see the loyalty of the fans in times of success, but also in time of worry and trouble.
Soccer, or football, is the most popular sport in the world, and FC20 is no exception. The club regularly attracts crowds of over 26,000, which for a city this size is no mean feat.
Founded in 1965, FC20 was a small-town club with big ambitions. And in 2010, those dreams were realized when they won the Dutch Championship.
They were excellent times, something that we could only dream of. It was just a crazy day for every fan.
Winning the league championship meant FC20 also qualified for the biggest cup competition in Europe. And their owners decided they needed a stadium to match.
The work was part of the club's development to create a stadium capable of holding more than 30,000 people. This would catapult them into the big league.
The plan was to extend the existing L-shaped section into a U-shape that was more than 45 meters long to accommodate nearly 7,000 additional fans. The cantilever-style roof would consist of 11 load-bearing frames, all linked together and supported by coupling bars connected to each frame at various points. Construction began in February 2011, with the assembly of the steel roof scheduled to start on May the 23rd.
The only problem was that the roof and the entire extension had to be completed for the start of the soccer season just over 2 months away. This was an ambitious project right from the start.
Professor of Building Engineering Robert Nies believes the impending deadline was adding extra pressure onto an already tight schedule.
Well, the usual thing in football stadiums, they take a long time to find all the money. And when they've done that, they want it finished tomorrow. It's always hurry, 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 because they have started the new football season. And when people start to work quick and there's no good supervision, which is very severe on the people, things go wrong.
With construction running behind and the beginning of the new soccer season quickly approaching, the unusual decision was made to work on separate parts of the stadium simultaneously.
When you're carrying out a construction on this scale, or any scale for the matter, there's a logical order in which things have to be done. But in the rush to get the project completed on time, that basic rule seems to have gone out the window.
People were doing things together in the same time while it was dangerous. There should always be someone, some external supervision who says, no, you may not work on the stands while they're working on the roof.
Because the concrete staircases hadn't yet been completed, the main contractor abandoned the original plans and had people working directly underneath the roof while it was still being constructed. This sounds like a recipe for disaster.
On July the 7th, 2011, as work on the steel roof at FC20 continued, and with workers still on top and underneath it, the entire roof collapsed onto the seats below. Photojournalist Eric Brinkhorst was one of the first on the scene.
I received a phone call when I was editing my pictures in my office. So I grabbed my gear and I drove.
Rescue workers were already on site trying to free people trapped in the wreckage.
There were some ambulances, there were people helping. The complete tribune was, of course, completely collapsed, so it was a harmonica of material.
Despite their best efforts, tragically, 2 construction workers lost their lives.
It gets emotional when something happens. Why us? It really hurts, and of course, it stays with you.
Many people knew of someone who was involved, working on the terrace or on the roof at the time of the collapse. Apart from the 2 casualties, there were many injured, and a lot of the boys on the stands are, also working in construction. So the impact was grave.
The tragedy sent shockwaves across the city and throughout the entire soccer world, and questions were being asked. Had the rush to get the stadium completed led to fundamental and fatal engineering errors? An independent report discovered that basic engineering rules and safety had been overlooked.
There's no actual problem with the structure of the stands and the roof itself. It's okay, it's well done, good executed, no problems. The real problems are during building up. It's not like by magic everything stands together. You have to work out the structure in a careful way, taking care that stability in all situations is guaranteed.
The main problem lay in the temporary support to the cantilever roof. Like any cantilever structure, the stadium roof requires temporary support, known as falsework, to hold it up until complete. In this case, they used temporary bracing in the form of steel cables to maintain stability during construction. The problems began when some of the supporting cables were removed to allow for work to simultaneously continue on the staircases and stands below, causing it to become less stable and, crucially, less strong.
They started adding the finishing touches when the steel roof structure was still very much under construction.
To make matters worse, they began adding considerable weight to an already unstable and incomplete structure.
And in this case, they made this big cantilevering roof on which they hang a television screen of 3,000 kilos at the end of the cantilever. So it's a big force blowing down.
The roof was subjected to an extra load of a video wall, suspension bridges, roofing sheets, and 10 workers. It simply couldn't take all that extra weight while it was still under construction.
The lack of stability combined with the massive overloading caused 2 central load-bearing frames to buckle and collapse, taking the rest of the roof with it.
This was one of the biggest failures, that they didn't make the precautions necessary to make the building stand up or the roof stand up during constructions. They did not do that, things collapsed, and then you got the progressive collapse. They wanted a big roof. And they got a big roof, only they built it in the wrong way.
The new section of the stadium was finally opened in early 2012. And new rules about safety and the use of temporary works were put in place to prevent any repeats of this tragic disaster.
Many of the construction workers were very proud of actually working on the club, working on their stadium, and as they said at the time, working on the dream. And obviously when this tragedy unfolded, their dream collapsed as well.
I know a famous architect who once said to me, a building is built twice, once on paper and once in reality. And if you don't do it right on paper, the reality won't work. And that happened in Twente.
In a rush to get ready for the start of the soccer season, it appears that vital things were overlooked. But a tight deadline must never be allowed to overrule safety.